Okay, I forgot to push record right when I started. So this is section 2.8, the derivative as a function. And I'm just going to move forward with where we are right now. The reason I like dy over dx as a notation is because it's more descriptive of saying who I am taking the derivative of and who I am taking the derivative with respect to. This is going to be, you're going to understand the value of this more later on in the chapter. The first test that I give you will not be all of, or the next test that I give you will not be all of chapter 3. What I do after the next exam, you will understand a little bit more why this is very, very valuable. But I want you to also see that notation as a noun. It is saying, hi, I'm a function. My name is dy dx. Whereas this notation is more of a verb and doesn't make sense by itself unless you put a noun in front of it. And I'm casually using English, whatever. But know that when you see just the D on top with nothing next to it, it is saying you need to take action on what comes after me, and you are going to take the derivative of it with respect to the variable x. These notations aren't used, I'm not going to be using a whole lot. I've seen them more in multivariable calculus being used. But we're mostly going to be using these guys in here. All right. Also, if you want to say, I am taking the derivative of the function y with respect to x, and then I'm plugging a into it, you can use these notations here. Know that it means the exact same thing as writing f prime of a. F prime of a says I already took the derivative, and then I plugged in a, and I know this to be the slope at that one point. All right. One of the things you're going to be doing in today's homework is sketching the graphs of a derivative function. This is very important to pay attention to what I'm about to do. While it may not be necessary for some of you to do this today, it's going to be in the future. And that is make a number line chart for f prime. Now, look at the graph of f of x. And let me just make sure that it's clear. This is f of x. Can you see where the slope is 0? You should see that the slope is 0 right about here-ish. Can you see a horizontal tangent line right there? And then right about here-ish, can you see a horizontal tangent line there as well? Sometimes you're going to know exactly what those x coordinates are. In this case, you don't. So what I'm going to do is I'm going to mark on this number line the approximate number that I think it is so that I can talk about it. So I'm going to mark down approximately 1/2 or 0.5. Then this looks like about 1.5. It's probably bigger than that, but I'm not going to waste my time trying to be picky about where exactly that is. Now, what this number line is doing is it's splitting the domain up into 3 sections. Later on, I'm going to include that not only do you need to write down where the slope is 0, you also need to write down where the slope is undefined, but you don't know what that is until later on in this section. In between where the derivative is 0 or anywhere that it doesn't exist, the slope is either positive or negative for that entire x interval. So if you look at the yellow section of the highlighted domain, do you see a positive slope or a negative slope? And you can mention it in chat. Let me put chat on. Positive. And I will be posting this video after class today. If I can write. There we go. Then in the pink section, do you see that from left to right, it's heading down, it has a negative slope. And then in the blue, it's heading up, it has a positive slope. Where f of x has a 0 slope, f prime has a 0 y value. It is the only y value you can be sure of when you're just looking at a graph visually. So I'm going to put 0.5 here just so that I have something. Ooh, maybe I'll make that line be 1.5. Haha. These are places where I know that f prime crosses the x-axis. And I'm going to label that I'm drawing f prime. Now, what each of the highlighted domain sections tell me are, when I am to the left of 0.5, I can't draw straight. I think I may need to, never mind. I need to be above the x-axis. My graph exists only where I'm showing you in the highlight. My graph has a negative y value, so it only exists down here in between the 2 points, x coordinates, and then only exists up here. There's only so much I expect you to see and be able to interpret when you're looking at the graph of f of x and you're trying to find the graph of f prime. What I absolutely expect you to see is what I've already drawn. You need to know the x-intercepts of f prime, and you need to be in the correct above or below the x-axis. Other than that, I don't expect you to be too exact on things. In fact, right now, you don't know enough to realize or recognize that at x equals 1, there is actually something special going on. I don't know if any of you see what I'm talking. I just erased something I needed to have. Okay. Erase. There we go. Erase. I don't know if you guys see what is going on at 1. Anyone take a guess? At x equals 1, can you tell by looking at the graph something important? No. You know what? We just aren't there yet. But let me say that the slope is steepest there as you go from 0.5 to 1.5. Can you visually see that the slope is steepest at 1? And if you are looking at your steepest negative slope, that is your negative y value that is furthest from the x-axis. It's actually a relative minimum on the graph of your f prime. You are not at the point yet where I expect you to see that, but I thought I'd point it out. And then other than that, we see that the graph gets super steep on the ends, and it probably looks about like this. If you are graphing if your function is polynomial and you take its derivative, unless your polynomial is a constant, you will get another polynomial. We're going to be seeing that tomorrow, actually. Now, also, I have on your homework assignment, I have a link to this derivative graph in Desmos. I think, no, was that it? Trying to find things I had pre-prepared to find. There it is. Okay, so this is the graph that I just showed you on the note paper. You can, using Desmos, graph the derivative. And again, I have a link to this specifically. Why would f prime graph be decreasing left of 0.5 instead of increase? Actually, this is f right now. I don't know if that's what the question was. This is f, not f prime. And let me see if, just hold on a second. Let me show this, and then I'll see if you still have your question. This is the graph of f of x. You can use Desmos, and you can play, and you can make any, you can change this to a different function. And I'm going to select, are you ready to see? Right now, g of x is deselected. I'm going to select it. And that is what its derivative definitely looks like. If you want to use Desmos in this manner, you have to name the function. Instead of doing y equals, use pretty much any letter you want. Some letters it has predestined. E, don't use E ever on Desmos unless you're using the number E. But you just need to name the function, name a new function, and this ddx, if you put, okay, I've got this thing covering it up, so I need to see if I can move this over. Okay, this is frustrating. So I'm going to have to bring it over here so that I can, okay. I hope that didn't stop recording. Okay, no, it did not. I'm going to bring it back now. Okay, in here you have a function menu. Under miscellaneous, right, do you see where the hand is? You can do ddx. But know that this is the way that Desmos works with creating it. All right. So you can put down any function you so desire, and it will immediately change the derivative graph for you. If you want to make up a function, you can deselect g of x, make it up, try to see if you can figure out its derivative, and then see, was I right? So that is a really, really beneficial tool that you can use if you have the time, of course, to play with it. All right, moving on. Also in your homework, you are going to have to find derivative functions using the limit process. And I want to say, again, not until chapter 3 do you get to use any shortcut formulas. You're just going to have to deal with it for now. We're solving limits while we're in chapter 2. We're going to go through this together. Using the second definition we learned yesterday, limit as h approaches 0, h in the denominator. And I'm going to write to the side that our numerator is f of x plus h minus f of x. For f of x plus h, I'm going to replace and substitute into that x plus h, minus f of x, which is root x. And I'm trying to color code for you a little bit so you can see that better. I chose this example because it's the one that if you don't remember the algebra that you need to use, you're going to be stuck. So I'm checking, why is h under the square root? The function is square root of x, and basically wherever that variable is, instead of writing the variable, put a parentheses if you need to, and then type in whatever it says to put in where the x used to be. Also, did I answer the question of what was f prime doing that I see in chat? If I didn't answer that question, please make sure to re-ask it. All right, moving on with this. Okay, good. There's a word for what I need to bring in, and I'm going to be looking over at chat in just a second to see if you remember that word. I see the word. Conjugate, yes. I'm going to do the algebra quickly here. If you don't know what I'm doing with the algebra that's about to show up, you need to take the time and work with it. And I'll explain what I mean in a second. So conjugate, just overemphasizing that the subtraction turns into an addition and everything else is the same. When I multiply conjugates together, beautiful things happen. If you don't understand what I write down, you need to do multiplication. You know how you do the box multiplication with root x plus h, that thing, blah, blah, blah. Do that on your own if you don't see why this works. And I'm going to keep going. Multiplying the conjugates together, I get x plus h, and then minus just x. Conveniently, we have x minus x. And even more conveniently, our numerator is now just h, and I can now do my 0 over 0 kill. Day, day! Numerator is left with a 1. And now I no longer have a 0 over 0 problem, and I can try direct substitution. My only h is right here. When I put in 0, I end up getting 1 over. And then I'm just going to simplify while I write it out. 2 times the square root of x. And that is the derivative function of root x. I pasted onto here the what your textbook does, and I forgot to mention the domain issue that it also asked for. The original function root x, you know the domain is inclusive of 0 to infinity. Yeah. And when you look at 1 over 2 root x, because the root is in the denominator, you should see that 0 is not included in the domain of f prime. Oh, you will always use definition 2 with the limit as h approaches 0 over h if you're finding the derivative of f of x as a function, because the other first definition uses the variable of the function in the limit, and that's a problem. Now, do you notice, you should note that the graph of root x is half a parabola. So can somebody tell me then, if that's half a parabola, how steep is the point plotted at the origin? Or, I'm sorry, how steep is the tangent line to the point plotted at the origin, right? It is infinity because at the vertex of a full parabola that's opened upward, slope is 0, and this slope is vertical. It is infinity. So you notice that that affected the domain of f prime. 0 is no longer in the domain because the square root of x is actually not differentiable at x equals 0. I'm going to put a pretty little asymptote there for emphasis. And this leads us to the question, how can a function be not differentiable at a point? And the word differentiable, we'll use that a lot. So my question is, how can f of x fail to be differentiable at x equals a? There are 3 ways. We just saw one of them. This is what I like to consider the does not exist continuum from the concept of what makes a limit not exist to what makes a function not differentiable at a point. The first thing that I have on this list is if f of x has a discontinuity at x equals a, it is not continuous at x, it is not differentiable at x equals a. This theorem here says if f is differentiable at a, then f must be continuous at x equals a. That is the same statement, just the contrapositive statement of what I said earlier. So let's bring back some memories. How can we fail continuity? We can fail continuity if our graph has a hole at x equals a. You are not allowed to take the derivative if you have a hole in the graph. It might feel like you should be able to, but you are not allowed to. Another picture is the same thing, but it could be defined elsewhere. Same problem. You cannot differentiate. So ways to fail continuity are these 2 plus the limit failing to exist. There are 3 ways for the limit to fail to exist. You probably remember some of those. One of them is that at x equals a, there is some kind of jump in the graph, or the left and right-sided limits do not equal each other. Another one is vertical asymptote at x equals a. And the other one we're not really going to run into so much because drawing it is ridiculous, but an oscillation. There's my oscillation. And this completes the continuum we started back in the days of limits. Now, another way, a way that you can be continuous, but your derivative does not exist, is what some people call a sharp turn. Some people call it a corner, but whatever you do on the AP test, do not call it a sharp turn or a corner. They don't want to hear you giving a graphical description when they ask you to justify yourself. If they ask you to justify, show, or any of those important words, you have to use calculus explanations. Describing the graph is not a calculus explanation. Saying that the slope coming from the right is not equal to the slope coming in from the left. This is the ideal way to justify this issue. Visually, we can see this difference as when we do have differentiability. When we zoom in on a curve, it gets straighter and straighter, becoming as straight as a line. If we are not differentiable at A, then it doesn't matter how much we zoom in, we will actually start seeing something that looks like an absolute value of X graph. Because if it is differentiable everywhere but that point, you're going to see what the tangent lines are over on the left and the right. But at the one specific X coordinate, it is not differentiable. Again, this is the phrase you need to be using on the AP exam if you are justifying that. And then the way we first saw was this, infinite slope. You are allowed to use the phrase vertical tangent line as a justification on the AP test because the word tangent line is a calculus word. Yay! Because that is a calculus word, you're allowed to use that phrase. So a vertical tangent line is going to occur if a one-sided limit, or maybe both sides of the rate of change are approaching either positive or negative infinity. And I'm trying to write 4 different limits as 2 limits by putting the plus or minus, because it's tiresome to even have to write it twice. But you only need to write one of these to express vertical tangent line. All right. Then we've got a little bit more to go. Is it okay if I scroll? All right, scrolling along. Oh yeah, my visual conclusion. That's in your textbook, figure 7, if you want to look at it later. And then, if I remember correctly, this is the last of the notes today. Higher derivatives, the notation that goes with it. If you already found dy dx, and you want to take the derivative of that, we call that the second derivative. You're not going to like this notation, but this notation has to do with that right there. Take a look at what I just circled in red. And can you see why they put the 2's for second derivative in different places? It's something you've got to get used to because you have to use correct notation if you choose to use this notation. That's why a lot of people prefer to just stick with F double prime. Much easier to write. Some of you know the physics idea of acceleration already. Some of you don't. Acceleration is the rate of change of velocity with respect to time. That makes acceleration the derivative of the velocity function, and velocity happens to be the derivative of the position function. So we can say acceleration is the second derivative of position, where S is representing position because we can't use D for distance or displacement because it's taken already. Now, as we go on to third derivative notation, I have a riddle for you. Okay. And hold off until I say writing the answer to the riddle in chat. So, what is the rate? Don't answer. What is the rate of change of acceleration with respect to time called? And I said wait. Because then I was going to say, if you don't know, here's a hint. There are t-shirts that say, don't be a that. Now it's supposed to help you see, what would be the same thing as telling people, don't be a blank, and acceleration changing. Ugh. What a jerk. That's right. You don't have to know that. It's just a fun piece of knowledge. Now, for third derivative, everything is the same. You can do 3 notches, shall we say, 3 prime symbols. You can say, go take the derivative of the second derivative, or just simply put a 3 in the same place that you had put the 2's. Now, these notations here, these notations here aren't essentially changing when we go to the nth derivative. As soon as we hit fourth derivative, though, we stop putting the primes. Anyone know enough psychology to know why we stop writing the primes after 3 of them? In a way, yeah. Supposedly, the average person psychologically doesn't need to count when they see 1 object, doesn't need to count when they see 2 objects, and the average person doesn't need to count when they see 3 objects. But apparently, on average, as soon as 4 objects are brought out, you apparently have to count to recognize 4. So for that reason, it's really bad to have 4 notches or 4 primes. It gets hard to read. So we stop using the primes and we begin writing a parentheses as a superscript with the derivative order written in that. So just to make sure you're clear, if I wanted to say fourth derivative, I would need to do that or that. And then it just keeps going with fifth and higher. I heard it's because our brain thinks multiplicatively. Maybe. Multiplicatively when counting. That would be something interesting to look up. This, let me double check before I say anything. Yep, that was it. This concludes our section 2.8 notes. Okay. Lions does not. Yeah, you know what? I'm trying to read chat, and I think it's not necessary right now because I need to focus and get you guys moving on homework questions. I'm going to keep recording for homework questions because people might want to look back at it. But if you just are watching the recording for the purposes of the notes, that's what I say. All right. Now, I know that I need to go over at least one of these problems right here. Do you have a preference for 31 through 36? And I can't recall off the top of my head which problems I assigned to you. 35. Okay. And I can go over more of them if you want also. You should notice that 33 is using the first definition. 35 is using the second definition. I want to first point that out. This particular set of problems is the most important one if your only concern is the AP exam. In the AP exam, you're not going to be taking derivatives through the limit process. You're going to need to recognize the limit as a derivative. You want to recognize for number 35 that this is f prime of a. What is f? What is a? Now the numerator is f of a plus h minus f of a. So you're trying to match that up. When they write these out, they on a test or a homework problem, They really are not trying to trick you like they do with some problems. I have always seen that they've been pretty reasonably kind about matching these up. This is probably about the hardest that it will get because of this plus right here, where you see a minus. But if you think about it, plus 1 is the same thing as saying minus negative 1. So more than likely, that's actually the issue. So I'm going to start by rewriting cosine of pi plus h minus negative 1. Where I have the a plus h, and actually I'm going to erase the highlights, or okay, it won't just erase the highlights, it erases everything. I'm going to change highlight color then. A plus h is going to be replaced by x to get f of x. Hopefully you can see that pi plus h is your a plus h. So that means you know that your a is probably going to end up being pi. From there, if this is matching the minus f of a, then that means that the entire function, and I'm going to change my highlight color, what would be pretty? F of a plus h is that entire statement. If you replace what you believe to be a plus h with an x, there's your function. So it looks like f of x is cosine x. You should double check to make sure that this tail end does what it's supposed to do. It is supposed to be f of a. So let's check. Based on what we think is f of x and what we think is a, this should be the cosine of pi. What is the cosine of pi? Yes, negative 1. And that is what we are subtracting. This works. I want you to know that there are other possible answers, but this is the most obvious one. And I'm not going to get into what else you could possibly write at this time. All right. Then I'm seeing you guys want problem 35, 19, and 20. I kept 14 up here because that one has been asked on a little bit, but let me go to find the textbook. And 35 was asked. Oh, that's the one I just did. Okay, 1920. Print screen. Copy. Am I? Okay. I'll start with 19 unless somebody says they know that they want 20 more than they want that. So I'm just going to highlight it so that you know what I'm working on. We're supposed to sketch a graph knowing certain information. I'm going to start with known points. F of 0 equals 0 is a specific point that must be plotted, so I'm going to plot that point. The next thing I'm going to do is look at what my slopes are and do kind of like little mini tangent line drawings. So this is not the graph, it's just drawing some mini tangent lines. F prime of 0 is equal to 3. So this point right here has a tangent line with a slope of 3. I am not going to draw it perfect, but that's a reasonable approximation. Got that done. When x is equal to 1, I'm going to put 1 out here. I know that I have a 0 slope. More than likely, if you had a slope of positive 3 at 0, that puts you above the x-axis. While it is not absolutely certain, it is likely that maybe you are located here at x equals 1. So I'm going to draw a little flat tangent line, but realize that it could be anywhere. I'm drawing a bunch of horizontal lines, and I'm trying to draw them for every place that x is equal to 1. Wherever you decide that 1 is located, wherever you decide the function is located at x equals 1, you have a flat tangent line. Then for 2, I'm being told that I have a slope of negative 1. So you can make a guess at where you think the point might be when you've hit x equals 2. It is a negative slope, so you had to head down to get there. But you can also draw a bunch of little negative 1 slopes all over the place where x is equal to 2. And wherever you decide to put that point, you have to have that slope. These are the only things that I know. So the only thing I know is that this red line is a vertical tangent line. This purple point definitely is a point on the graph. And other than that, somewhere along here, I have a 0 slope, and somewhere along here, I have a negative 1 slope. Now, did it say this was a function that was differentiable everywhere, continuous everywhere? No. If you have a multiple choice question that asks you what must happen, be careful. Most people, however, are going to draw a graph that basically goes la 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 la, la la la, la 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 la, maybe something like that. It's going to vary from person to person what it looks like when you draw it. You just have to have those 3 things. All right. I'll more quickly go through number 20. I have one known point at when g of 0 is equal to 0. One known point. Let's look at slope information. I know that the derivative of g at 0 is also equal to 0, so it's a flat horizontal tangent line. When x is negative 1, I know that I have a negative 1 slope. I'm going to draw a vertical line of a bunch of negative 1 slopes. I'm not perfectly drawing them. For g of positive 1, I have a slope of 3, so it's a positive slope, decently steep, but I don't know where the point is located at x equals 1 necessarily. Those are all supposed to be parallel. Yeah. Then, when x is equal to 2, the slope is 1, so I'm going to draw about a 45-degree angle, but I, again, don't know where that point is. From there, anything goes. It didn't say the function was continuous or differentiable everywhere, so you can draw whatever you want. I'll just kind of draw what is most likely to be drawn. 5-minute warning. So most likely I'm kind of coming down and going, ooh, flatten, go up, very steep, and then, ooh, slowing it down a bit. Something like that. But there is a crazy variety of what you could come up with. Okay. Then are there any other particular homework problems you want to see? Because we do have 5 minutes. Yep, that's what I thought. 14 was a problem, shall we say. I'm going to erase what's around it to not distract it. And I'm going to delete. There we go. Okay. The function h of t is representing height in meters after t seconds from the planet Mars. Hey, any of you think you might actually go to Mars in your lifetime? I see some wishful thinking in some of your faces. Okay. Now, they want you to find the velocity of the rock after 1 second. So they're asking you to find h prime of 1. They didn't say which definition of derivative to use. So I'm going to go ahead and just use definition 1. And I'm going to use variable t because h is using variable t. So the limit as t approaches 1 of the function h of t minus the function's value h of 1 over t minus 1. H of t is 10t minus 1.86 t squared minus, and then we need to find h of 1. Oops. Very aggravating when it thinks I clicked on something else. There we go. So right here, I need to plug 1 into those t's, and that gives me a number. And that number is 8 point. Who wants to write the answer in chat? Thank you. Now you're expected to solve this limit from here. That means when you look at it, you have a quadratic over a linear polynomial. You need to factor the numerator so that it will cancel with the t minus 1. The good news is the denominator is giving you a hint. If I have 2 polynomials and I plug in 1 to both and I get 0, both polynomials have the factor t minus 1. So for this quadratic, you need to figure out what you get if you divide this by t minus 1. I'm not going to spend the class time going into it. If you need to, you can do the box division. If you recall that, the polynomial, the quadratic of the numerator needs to go in these boxes, and you've got to figure out what these two are. And I'll leave that to you. Once you're able to do that, these will cancel, and you'll plug 1 into the t that you get in that other factor. Be very cruel. I wouldn't do the algebra myself. It's just awful. You're doing the exact same thing as you are here, either using definition 1 or definition 2, but thank you. But it's awful. So let me just say, feel free to go to your solution manual for help in the nastiness of that. With part C, The rock hits the surface when h is equal to 0. So that's not too bad of an equation to solve. 0 is one solution. You're looking for the positive solution. Then in part D, you're going to use what you found in part B, and you're going to plug whatever answer you got in part C into the A, and that will give you that answer. Other than that, anything I'm not showing you here about the problem, you're not going to be tested on, because the issues are more in the algebra than they are in setting up the limit. What was the velocity equation? I need to look the answer up real quick. And it is time for you to go, so I can't hold you. If you want to stay in, you can. I can look up the answer. Okay, I gotta find. Again, you are absolutely free to leave. You are absolutely free to leave. Where is... Now I'm just trying to find. Okay. Da, 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 da. Da, da. I'm really frustrated with slow internet. The internet really needed to know COVID was coming and get better. But okay, why can I not? Why? What? Oh, I apologize. This is taking too long. Just trying to get to the solution manual. Probably about here-ish. So that's 2.8. Looking for 2.714. There it is. This is the hideous algebra. It is something I wouldn't ask my enemy to do. No, wait. I take that back. I can think of one student throughout my years that I would make do this for fun. Oh dear. But this is the whole thing. It is not simple algebra. And it is, the factoring that's going on there is not. Well, then again, it's just a lot of work. You do end up getting some cancellations, and that's what makes this doable in the end. But it's just way too much work to for you to sit here and watch me go through. And then that gives you wind up with this formula. And then in C, when you solve this equation, you end up getting approximately 5.4. Plug that in, and then you've got D. So always feel free to use the solution manual. I have it posted for this purpose so that you guys can help yourselves to learn. Okay.
So h of t acts as f of x in like for the limit definition?
Yes. Yeah. Mm-hmm.
What formula is being used in part D?
Oh, for D, it's using the results that were already found. So this is what you get in part B if you go through all that lovely algebra. In part C, you solve for when h is equal to 0, and you get this time. So you take that this is the velocity at time A, and this is the time you want to know the velocity, so you plug 5.4 into the A of this, and that's where that whole piece right there is coming from.
So the quiz tomorrow is just going to be based on like pretty much what we learned, like the homework from last night?
Oh, yeah. And know that I've got to make a quiz that you can do in like 10 minutes. I think that says a lot right there. A good question for a quiz would be like one of these, but with multiple choice. So with multiple choice, I could say which of the following f of x a combinations could this be the derivative for? So if I write it, I would actually express this entire piece that I'm circling. I would even say this is equal to f prime of a. Which of the following are the f of x and a for which this is true? And then only the most obvious one would be the correct answer. Incorrect answers, I will admit, are ones that people will fall for. And you can do more of, there are 6 problems here that you can look in the solution manual and study with. I don't remember how many of these I gave you for homework.
You give us 2, 31, 30.
Okay. So your best way to study for the quiz is to check and see problems that weren't assigned near it. Can you figure those out?
Okay.
Thank you.
Uh-huh.
Thank you, Miss Blanchard. Have a great day.
You too.
Tomorrow.
Bye-bye.